So we're going to derive the second equation of stellar structure, the so-called equation of hydrostatic equilibrium. And the law of physics we're essentially using here is Newton's first law of motion, right? If the forces balance, then there is no acceleration. In other words, the object is in equilibrium. Now we observe on astrophysical on timescales shorter than astrophysical timescales, so on timescales of a year, 10 years, 100 years, 100,000 years, our sun is not changing. We know that it is not expanding or exploding, so the forces inside the star that are pushing outwards are not overwhelming the forces that are pulling stuff inwards. We also know that it's not collapsing or shrinking. So the forces inside the star pushing outwards are not being beaten by the forces pulling inwards. Right? So in other words, the outward forces balance the inward forces. So we just have to write down expressions for those two oppositely acting forces and set them equal to each other, and we will get another equation. So let's draw a zoomed in look at one of our spherical shells of matter. Okay, so let's say it has a thickness dr like we did before. Now the forces acting on this shell are the force of gravity, which are pulling the spherical shell inwards, and the pressure force pushing it outwards. And the pressure force comes from the fact that the pressure acting on the bottom of the star, the bottom layer of the star is slightly larger than the pressure pushing down on the top layer of star. Okay, so there's the pressure up here is slightly less than the pressure down here. That has to be the case for any self-gravitating body of fluid. Okay, what we're going to derive here is just as valid for the Earth's atmosphere, and it's just as valid for a swimming pool. Right? In a swimming pool, when you dive down, you notice that the pressure increases as you go downwards. And that's because the pressure has to support an increasing mass of water above it as you go deeper into the swimming pool. Pressure has to increase, otherwise the water would collapse inwards on itself. So the equality of the gravitational force pushing inwards and the pressure forces pushing overall, a net pressure force pushing outwards, this equality is called hydrostatic equilibrium. So we need to write down expressions for these forces. Newton's law of gravity provides an expression for the gravitational force. Remember, it is valid for spherical objects, not just point particles. And it is equal to minus g times the mass inside of radius r. Let's remember that this shell is at a radial coordinate, little r. And the mass below it is m of r, so that's the mass causing the force to pull the spherical shell inwards. Then it's multiplied by the mass of the shell itself, and we divide by r squared. Okay. We've encountered dm before. It's just 4 pi r squared rho of r dr, and then we're dividing by r squared here. And I'm not going to cancel this at the moment for reasons that will become clear. Okay, so what about the pressure force? Well, pressure force is equal to pressure times area, right? So the pressure force acting upwards on the spherical shell is equal to P plus dP times the surface area of the shell, 4 pi r squared. And then the force acting in the other direction, pushing down on the top layer of the spherical shell, is P times the surface area. And because we're dealing with an infinitesimally small shell, then as dr tends to 0, the surface area of the bottom is equal to the surface area of the top, which is 4 pi r squared. So this P times 4 pi r squared is going to cancel this P times 4 pi r squared to leave 4 pi r squared dP. Okay, so we're going to have to set these two forces equal. And if we do that, notice that the 4 pi r squared here and here are going to cancel, and we're going to get dP is equal to minus g m of r rho of r dr divided by r squared. And if we divide by dr, we get the equation of hydrostatic equilibrium. dp by dr is equal to minus g m of r rho of r over r squared. Okay, so we can write this down underneath our first equation of stellar structure. dp by dr is equal to is equal to minus g m of r rho of r divided by r squared. Okay, this is the equation of hydrostatic equilibrium. And there's another differential equation in this form like dm by dr. So we've now got two equations of stellar structure. Remember, we're looking for three unknowns at the moment, so we're going to need a third equation, which we will come to in the next lecture. And keep in mind what the physics is behind this. It's very, very simple. This is just conservation of mass. This is Newton's first law of motion. That's all the physics that we have put into it at the moment.